He will tell us about complex cobordism method, modulo c₁-spherical cobordism and related genera. So please welcome.
Thank you. First of all, I have to say that I'm happy to be in this nice conference, to see again Victor Matveevich, and I'd like to wish him the very best. Long, healthy, and productive life, just continue in the same spirit. Thank you. This is some material from my new paper. So this is instead of website. So please comment if you will see some types of mistakes. Talk about results, which is based on the previous work papers by the following authors: Bushtaber and his students Smolkova, Busato also his student Chernych, you'll know each other, Kholodov, Khyov, Nadiradze, Panov, Totarov, Ustinov, and Vershini. So it is proved here that the ideal incomplex cobordism, which is generated by the polynomial generators ZS of the c₁-spherical cobordism ring, we have these elements in MU by forgetful map, is prime. This means this sequence is regular and quadrant ring is integral domain. Then by using the Bar-Sullivan theory of cobordism with singularities, we prove that all the Mironov obstructions to the commutativity vanish, and we define a commutative complex-oriented cohomology theory, which I call complex cobordism modulus c₁-spherical cobordism. It has coefficients which is identical to the quotient ring mu by this ideal S. Then any subsequence of this sequence S is also regular in mu, and therefore gives a multiplicative cohomology. Which in some cases the commutativity is a question yet, but they are complex oriented, and it's denoted by the symbol mu sub sigma. We prove that generators of W star, if we invert 2, can be specified in such a way that for sigma here, if starting from K, if omit first generator, then it corresponds to Abel cohomology, which previously was constructed by Busato. And another example is subset starting from K greater or equal 5. And again, if inertic 2, the coefficient ring is the universal Buchstaben-Formal group law, and rationally it's identical to the Ricciardo complex elliptic genus. So in this particular cases, we just have agreement with known results. And what follows is some parts of this paper in functions. First, let me give statements in detail. The complex cobordism and special unitary cobordism, of course, play an important role in cobordism theory. And MSU, after inverting 2, is torsion free, and has generators in all dimensions starting from 2. The y2 is the dimension 2, 4, and so on. And if apply SU structure forgetful, we have inclusion in complex cobordism, and so that the generators wise can be treated as elements in mu 1/2. In particular, this wise, what is SU manifold? Manifold if all chair numbers of y's, which is as factor c₁, are 0. So the tangent bar, the determinant of the tangent bar is trivial. There is Novikov's criteria for membership of the MSU manifold. We will apply this below. Now, c₁-spherical cobordism was introduced by Conner and Floyd. It's denoted by W. And a complex cobordism class belongs to this group if and only if chair numbers, which involve c₁ square, vanish. It means that determinant again of the tangent bubble is classified to the map of sphere, to sphere, which is two skeleton of complex projective space. So determinant always classified to map with CP infinity, but in this case, particular case, map is in two skeleton. So it's well known that W star is not subring in mu star, just subgroup. However, there is some complex orientation and some multiplication such that W star is polynomial ring and generated by the symbols in all dimensions but only 4. And this is references to works by Taras Panov and his co-authors that polynomial generators can be arranged in such a way that main chair numbers S, K, X, K will be as follows. We will need these main chair numbers, of course. So if invert 2, then W star 1/2, not only complex oriented, but it's actually generated by coefficients of corresponding formal group law, which is not true in integral case. It is also result by Taras, Panov, and Chernykh. Oh, our main observation is that the polynomial generators of W star, if it's polynomial and for second orientation, viewed as elements in mu star by forgetful map, generate the same ideal in mu as coefficients of formal group laws alpha ij with this property that I and j greater or equal to. So those two ideals coincide. But if okay, if invert 2 Yes, we have for sure we have to invert 2 here, but if not invert, this is the question. Don't know if this new results. I don't know. But anyway, if we factor by this idea, this also regular sequence and gives some theory, not exactly Abel cohomology, but something which with the isomorphic scalar ring. But if we want that classified maps also agreed, then we have to invert 2 for sure. And maybe we don't, I know. So this is main theorem. So here all the x's, x1 and x is starting. So we do not have x2 here as generators of W star. So if consider this S is regular in MU star, and any subsequence of this is also regular. And again, then we are going to this Sullivan theory. It's cobordism with singularities and define multiplicative cohomology theory. And then we have to prove using the results of Mironov that all obstructions vanish. That is, this theory is commutative. Here without inverting O2 even. Again, two interesting examples are the Abel cohomology with inverted 2 and this ring which gives the universal Buchstaben formal group law after inverting 2. In this case, we know that universal Buchstaben formal group law has 2 torsions, so we have to invert 2 or kill torsion because this torsion part is the obstruction to define the cohomology theory. So in both cases, it's possible. So at that in that section, we have to we can consider the restriction of this genus on this ring W star itself, and so that we obtain some genus on W star from W star to this polynomial with the integer coefficients with some 3 parameters, x1, x3, x4. Okay, then here is what Taras asked already. But again, in case of theorem 1.4 and 1.3, the question of commutativity is open. Now, let me just give some general idea by just following this text. So, SU with inverted 2 is polynomial ring, but we have to, we will need this specific generators here because in order to prove that two regular sequences generate the same ring, same ideal, we will process by induction that we need that initial terms agreed. So this just we can present the generators as elements in complex cobordism, and we have to just calculate this and all chain numbers and see that all chain numbers which are in all C1 are 0. This is that Y2, Y3, and Y4 actually are special unitary manifolds. And we will need also construction by Panov. It's quasi-toric manifolds, because he proved that in MSU, a special unitary cobordism by with inverted 2, the generators starting from 5 can be arranged as quasi-toric manifolds. And that Krichever of elliptic genus vanish on these manifolds. This is the reference to the specific work with specific theorem. And also Totaro has some result which with the flops, SU flops, with the quasi-toric manifolds replaced by so-called SU flops. The same theorem is true, that generators starting from 5 can be chosen as SU flops, and they are vanished under whichever elliptic genus. And what is whichever elliptic genus? This is also called Krichever-Helm genus, because previously Krichever was now wrote down as characteristic power series Q using Baker-Kaiser functions, but Helm gave another definition in terms of such property that if H is denoted by exponent prime over exponent, then H should satisfy this differential equation, where S is submonic polynomial of degree 4. So from here we see that rationally coefficient ring will depend only on 4 parameters, P1, P2, P3, P4. But in works of Buchstaben and Christo, I think this is reference to Buchstaben Bronkova. They introduced this formal group law. Here definitions. W is the invariant differential form of Fk, and beta is this expression. And call this formal group law universal Krichever formal group law. And one lemma is that this formal group, the exponent of this group Fk satisfies condition here. It means that classifying space Ck is specialization of Krichever genus. It can be classified from the universal one. Also, consider this formal group of this form, and where A and B satisfies this properties, and if we add that A prime 0, B prime 0 are equal, then B will be necessarily the invariant differential form of formal group law. And this formal group law is called Buchstaben formal group law, and the universal formal group law with this property is called the universal formal group, universal Buchstaben formal group law. Oh. If we ask what is the classifying map for the universal formal group law, it can be defined as follows, just some trick. Take the universal formal group law and multiply by this expression. W here is invariant differential form of the universal formal group law. We obtain some series in AX, Y. And if we kill AIJs with this property, both greater or equal 3, we obtain some quotient map from MU to some quotient ring. This is exactly the classifying map of universal formal group law, of the universal Buchstaben formal group. So that this formal group law, universal one, here, classified by this quotient map. Okay, this quotient ring is very complicated. It was computed by Buchstaben and Ustinov. Here is reference 11. Infinite limit generated, not polynomial, but what is good that it has only two torsion in some dimensions, and if we invert 2, the torsion will disappear, and we have now two ways: invert 2 or kill torsion, and then continue to try to construct cohomology theory with this scalar ring. Now something about c₁-spherical cobordism again. So again, here is reference to Buchstaben work and I think Stone about projector from MU to itself. And what is W star? W star is just image of this projector. And in W star, we can introduce introduce it in this paper, star, another multiplication with this property. Here V is cobordism class of the coefficient of formal group A1, 2, or as element in MU star, this one. Then W star is just subring in MU, but it's a ring with respect to this multiplication, and in some orientation, W star is polynomial and generated as we had before in every positive even degree except 4. Now Abel case, Abel formal group law, by definition, F Abel is formal group of this form. So you see that all alpha i's coefficients are 0 if both indices greater or equal to. Mhm. So this is universal case, universal formal group law, which was introduced, of course, by Novikov, and by him and Quillen proved that the ring, coefficient ring, agrees with Lazard ring, so that it's universal one and every formal group law can be classified. In this case of Abel formal group, we have again classifying map is just quotient map, which kills this coefficients. So the term Abel formal group introduced again by Buchstaber because of this very old work by Abel, where he considered some functional equations and somehow has this form. I never read this, but Buchstaber named his formal group as Abel formal group. So again, this ring also complicated, and as a ring also was calculated by Buchstaber and his student Holodov. And again, this ring is torsion-free, integral domain, and rationally, it has two parameters only. That is, associated equations rationally express all CP. Rationally, MU is generated by complex projective spaces. So two parameters, first to CP1 and CP2 is parameters you can consider. And all upper CPs are expressed by the CP1 and CP2 rationally. But integrally, the ring is very complicated, virtually infinitely generated and non-polynomial. Here are some combinatorial definitions which we need to apply the Euclid algorithm to choose generators of the ideals we need. So we have many elements, and somehow we need to construct by them some elements which is minimal in order to get minimal number of generators for ideals. So this is very known identities. Here just references. For instance, this DIM, then this is actually the criteria of for polynomial generators in MU. So generators of MU satisfy this, depending on dimension. In this process, we need that not only classifying not only the rings of universal formal group law, Buchstaber formal group in case of whichever Helm, genus, or in case of Abel formal group law, are integral domain. But they are integral domain if we factor by sub-ideals up to some level L. For example, AB is full ideal generated by all alpha IGs with indices 2 or more. But if we put here L, this means that this ideal generated by elements with degree less or equal L, not all alpha. We need this in order to apply induction on dimension. So many theorems here are proved by induction. Here is just very standard things from algebra. That what is the definition? What is integral? What is regular sequence? And in case of ring is polynomial and generators of the sequence are homogeneous, we can transform them or take any subset and again get from regular sequence, again get the regular sequence, which is not true in general. But in our case, everything is okay. So we can freely, if we have regular sequence, we can transform or omit some and take any subset and get again regular sequence. For instance, for the demonstration, this is one of main lemmas, which says that say GW be the ideal mu generated by this element Y2, which is this is the product in c₁-spherical cobordism. And as element in mu, this is can be written as follows. So generated by Y2 and generators starting from 3. So, and GWL, the same, but up to L, okay? And I and IL, as it was in case of Abel. So it turns out that we have one which says that JWL, Abel plus one more ideal Y2, one more element. So ideal by Abel plus one generator, Y2. And if we add this Y2, again we get regular sequence in mu. So Abel's in Abel's case we had regular sequence. We just add one more element Y2, which is again regular. This proved by actually there are two ways. One is to follow Busato's long through. Victor Latovic knows this. This was Busato's dissertation. And in this particular case, we somehow can, in some places, simplify this proof. And idea the same. We need the groups, the construction of groups, and main chain numbers of generators, and apply induction. Okay. So that we first take, shortly saying, Abel's ideal, add one more element, prove that it's again regular, then remove this element and add first one, x1. So that we proved this original theorem, but if before adding z1, we cannot say that this theory is commutative. So if start again from z1 or x1, the ideals we cannot say that they agree, but both sequences are regular. So maybe they are agree or not, but after inverting two, they do agree. So that's why we had the theorem before that in order to agree, this example with Abel's case, we have to invert two. This theorem says that in case of our main theorem, we can prove that all obstructions vanish. This is proved using Mironov's work, where the constructions for obstructions, there, in this case, vanish. So that, if we have this full this one, all the generators of W star, so that mu star, again, the main result is mu star, quotient by the ideal generated by W star, gives commutative complex-oriented multiplicative cohomology theory. And let me call this complex cobordism modulo c₁-spherical cobordism. This is actually the paper which I want to submit it already to this conference. And after correcting some typos, maybe so proofs, let me omit proofs in details because it's very technical. And now about, okay, this is just, you see how it's in some sense routine to calculate this, the main chair numbers of the initial terms of this in ideals, y2, y3, y4. And finally, if we restrict this 4-parameter genus on W star over 1/2 with inertic 2, as W star has no generator x2, we have this genus from W star 1/2 2 polynomials with integers in these 3 parameters. And references, you see that lots of works by Buchstabe and his students. It's 8, 9, 10, 11, 12, 10, 14, 15, and so.
Thank you very much for interesting talk. So please questions if any. or comments?
In your talk, you mentioned several formal group laws introduced by Buchstaber and other people. Those formal group laws have rather big coefficient rings. And if you specialize those coefficient rings, you will get formal group laws over fields. So what heights of those formal groups would you get? Would you get anything other than 1 or maybe 2?
If you want to get smaller coefficient rings, for instance,
A field.
well, the very first theorem, its coefficient ring large, but rationally it's polynomial in one variable. Rationally. After tensoring by rational numbers, you will get polynomial in one variable.
That's not my question. If your coefficient
but
ring,
if you construct some typization and after this, like Brown, Peterson, and so on, yes, okay, or you have to look at formal group laws and look at coefficients in some specific powers, yes, like Morava theory, yes. You ask about heights, yeah?
yeah. What heights will you get? Will you get 1
What
or
height
2?
in complex cobordism?
Well, any height.
Okay.
Yeah. So will you get any height
Yeah.
here as well? So
Yeah.
can you get by specialization height 1, 2, 3,
Yeah.
etc.?
Yeah.
Okay, right.
Okay, more questions, please. Comments?
So that, just to make sure, so that when you take the quotient of the mu theory by the W theory, and you say that that particular
We omit general in dimension 4, yes?
yeah. So that result about the formal group law in the resulting theory, that holds over with 2 inverted.
Integrally.
Integrally.
Yeah.
Okay.
If we take all generators, but if you take subsets, then you get again integral some theories, but we don't know if they agree with the known ones.
And you also don't know if they are multiplicative, right? Apart from the
Yeah, multiplicative, but maybe not commutative.
oh yeah, sorry, not commutative. Yeah, that's what I mean. But the one that you get by multiplying by the whole ideal of W theory, is commutative.
Yeah.
Okay.
More questions? If no, so the same speaker again. Thank you.
Thank you.
Малхаз, замечательный доклад.
Спасибо, Владимир. Спасибо.
So the question or comment? Yes, so we resume in 10 minutes.